Today I wanted to talk about quasiperiodicity and fractal structure may appear in continuous phase transition, either quantum or thermal phase transition. So I will first give a brief introduction to quasicrystal structure, and then return to Penrose lattice and try to classify vertices, and then I will use this concept for further analysis of the physical phenomena. Specifically, I will consider Bose-Hubbard model and look at the emergence of the quasiperiodicity effect in the phase diagram. Then I will return to Ising model, and then I'm looking to see any difference between Bose-Hubbard and Ising model, because here I will discuss about thermal phase transition, and then I will bring my study of the Monte Carlo simulation of the Ising model, and then at the end I will conclude my results. So as a brief introduction, we can classify different structures based on the aperiodicity that they have. First of all, there is the crystal. We have a crystal that they show Bragg reflection or diffraction pattern, and we have amorphous system. They don't show any diffraction pattern, and quasiperiodicity. So I don't know how. So this structure, although do not have any translational symmetry, but has a local pattern. But if we increase our view of the pattern, we can see the difference between the patterns. For example, if you consider these patterns, you can see they are similar. But if you look at the farther region, you can see there is a difference between these patterns. So I will consider distinguishable patterns in my work, and we will see soon that they have a very deep effect on the phase transition, maybe. So I wanted to talk about continuous phase transition in quasicrystal. So here we saw that we can see this repeated pattern of some structure in quasicrystal. Then the question is that which length control this distinguishing different patterns? We know that in phase transition and continuous phase transition, there is a length that diverges in phase transition, which we call correlation length. So we want to know that is this length change the universality class, or is this length introduce new exponents in quasicrystal or not? So I will mainly focus on Penrose lattice, which can be constructed by changing tiling to vertex model, where I use vertex of the tiling as a site of bosons, in future bosons or spins that are living in these vertices, and the coupling given by edge of this tiling. This Penrose lattice has a lot of properties, which I will not discuss about it. First of all, before I am going to show my results on Bose-Hubbard model or Ising model or other systems, I will first want to give an introduction to classifying each vertex in Penrose lattice. So we can classify, because in quasicrystal we have a different coupling between sides. We can classify each vertex based on its coordination number. The coordination number is the number of links that connected to a specified vertex. For example, here we have a vertex with 7 coordination number. You can see count 1, 2, 3, 4, 5, 6, and 7 coordination number. Therefore, we can label each vertices in the Penrose lattice with 5 different numbers ranging from 3 to 7. Therefore, we have until now we can classify each vertices based on 5 groups. So I wanted to know, is it possible to increase this classification or not? So if we look at sparse vertices, we can increase our subclass to higher number of classes. For example, consider here I show vertical number is 7, and look to the number of the vertices with a specific label. For example, here I label 3 link site vertices by 3. So if you count them, you can find there is a 6 different 3 link vertices connected to 7. Then write somewhere that in 3 link, we have a 6 3 link vertices nearby these 7 vertices. Then find other vertices by 1 path around this specified vertices. Then you can find there is no 4 vertices around these 7, for example here, and there is just one vertices with label 5 here. So you can summarize this number as a code and label each vertices with this code. So by this manner, you will find 14 new class of vertices, which I table it here. So for example, 7, which I consider it now, written here. And you can see by doing this, we can classify each vertices in Penrose lattice. So we can increase this procedure for further. For example, in the next step, we construct a cluster of the vertices that can be constructed by 1 path. For example, here we reached as 3, 3, 3, 3, 3, and 5, and then look at the connection to these vertices. So looking at the nearby vertices and the 7, and count now the number of vertices labeled with their coordination number. For example, if you look at the 3 vertices here, you can find this cluster connected to 1 3 labeled vertices, and here also 1. So there is 2 3 labeled vertices. So you can generate new code, and then by doing this and also combining these 2 codes together, you can distinguish 27 different vertices in Penrose lattice. You can increase this classification of the vertices if you increase the number of the paths that considering vertices. For example, if here I consider more further vertices, and then write a code for the 7 structure, and then right here, and then combine this code, and then I can find a higher number of the classified vertices. So here I show the configuration up to second link. So this is the first link configuration, and this is second link configuration. So totally by second link, we can construct 27 different structure. You can distinguish 27 structure in Penrose lattice. So here I prepare different vertices that we can find by this procedure. You can see nicely this classification distinguish different structure in Penrose lattice. For example, it includes several three linked vertices and further subclass of this structure. Interesting things is that we know that we can construct Penrose lattice by cut and project method from 5-dimensional lattice. So in this sense, we introduce a perpendicular space. So If we label it each vertex with the new subclass that we find in previous slides, so we can find that we can find that the vertices with similar label can map to some specific closed region of the perpendicular space. For example, if you look at the one, all of them map to this part of the perpendicular space. So this classification, it seems this classification is natural for perpendicular space. So we can, as we see, we can extend this classification to infinite number of the infinite length of the, looking at the infinite length around each vertices. So in this sense, this is a very natural classification of each vertices, and we can see that perpendicular space is nicely divided by this classification. So as I said, we can increase this classification by increasing the path which we look at around each vertices. This number of class grow if we increase this, considering the vertices around the specific vertices. Interesting thing is that the number of class increasing by power law behavior. I did this for other quasicrystal structure, and it seems that other quasicrystal structure has a similar power law, which by increasing the path, by increasing the length of the looking at around of the vertices, the number of the class will increases by power law. And interesting thing is that in one-dimensional for Fibonacci lattice, we have also similar behavior, but almost its exponent is half of the 2D dimensional case. So now let's go to study this model. A model, and show that what is the effect of this classification in a phase transition. So as a study case, I consider here Bose-Hubbard model, which is hopping of the boson, which controlled by this term J. This is hopping strength that one boson inside J annihilated and created inside I, and a chemical potential which controls the number of the boson in each vertices, and interaction term, Hubbard interaction term, that describes intra-site interaction between bosons. So we cannot solve this this Hamiltonian simply because these two terms are not cannot be solved simultaneously. Therefore, we have to perform a mean field approximation if we want to study very large system that capture quasi-periodicity of the system. It seems even in mean field approximation, we can see much superfluid phase transition of this Hamiltonian. So what we can do is that we treat the first term in a mean field manner and translate this Hamiltonian to local Hamiltonian. By doing so, you can find a self-consistent equation that that both should be satisfied, and then continuing the updating the parameter of the self-consistent equation, you can reach at a convergence, and then you will be find a state of the system in mean field manner. So this system I study for a lot of systems. For this Hamiltonian I study for a lot of systems. For example, in homogeneous system, ordinary system with a translational symmetry, and other structures. And it seems that there is a universal somehow phase diagram if we neglect disorder and nearest neighbor interaction, just looking at the Hubbard interaction and this term, this Hamiltonian. We can see a somehow universal phase diagram, which we have two different phases, matte phases and superfluid phases. In matte phase, matte insulator phase, there is a gap, and all of the site has occupied with one boson, one integer boson, and but in superfluid we have a there is no integer filling of the site, and the site has a different, I mean, integer filling, and overlap of different integer filling. The specific feature of this phase diagram is the appearance of this dome shape in the phase diagram. So I want to know if we change the structure from periodicity to a quasi-crystal structure, is everything changed or no? So because I want to reduce the boundary effect, I will work on periodic boundary condition. So for performing periodic boundary condition, I will use a unit cell of approximant. Approximant is a periodical approximation of the quasi-crystal, and then I took one unit cell and then identified two different edge of this unit cell of the Penrose approximate. So by doing so, you can find the phase diagram of the Bose-Hubbard model in Penrose quasi-crystal. I use this number of around 100,000 sites for my calculation, and find this phase diagram for the Penrose lattice. This orange one is the critical strength of the matte superfluid phase transition for the square lattice. So here we have a matte phase, integer filling of the bosons in each vertices, and here we have a superfluid phases. You can see that increasing chemical potential just increase the number of the occupation number in matte insulating phase. But here, if you compare the phase diagram with square lattice and Penrose lattice, you can see that there is no, significant change between these two different structures. So it seems that introducing a periodicity did not change, anything in phase diagram. It is actually the shape of phase diagram is reasonable that why it doesn't change, because in Penrose lattice the average of the coordination number is 4, and in square lattice we have also coordination number for all vertices, which is also 4. Therefore, maybe we can expect before the calculation that phase diagram should not change significantly. But this is not the whole of the story, and we can, if we look at the distribution of the order parameter, you can find more interesting things. So here I show for this line, this chemical potential from the phase transition to large J, the distribution of the order parameter or superfluidity amplitude for each kind of these vertices. For example, here I calculate order parameter for all vertex labeled 1 and represent it here. I did this for 27 different vertices and show the plot here. So you can see at the end of at the large J over U, all of the superfluid amplitude, average of superfluid amplitude in each vertex class group together to become finally five different groups. This is exactly the number of the coordination number of the different coordination number in Penrose lattice. But when you approach the phase transition from here, from superfluid to multi-insulating phase, you can see they degroup. I mean, the group structure destroyed, and they find different value of the superconducting pairing. So if you carefully look at the near this phase transition, I also show some bar which indicate how much the average, how much this distribution of the amplitude of the superfluidity distributed in each vertices. For example, by looking at this is actually a standard deviation of the superfluid amplitude in each classes. So you can see by approaching the phase transition, this standard deviation somehow increases. So it signals that in each vertex class, I mean, label it vertex class, for example, 1, we have a different, the different structure also may emerge. So if you look at the order parameter distribution in the real space and in perpendicular space, you can notice different behavior near phase transition and far from phase transition. If you look at the far from phase transition, you will see that the distribution of the order parameter, specifically in perpendicular space, has a handful of the color. So it seems that there is, for example, 14 different colors of the superfluidity amplitude. But if you look at the phase transition, look at near phase transition, you can see a fractal structure appear in the phase transition in perpendicular space. It means that if you remember that by vertex classification, the perpendicular space divided by different sections. So this fractal structure means that the superfluidity amplitude is depend on the vertices, different vertices. It means that, in other words, means that each vertices in Penrose quasicrystal now has a different superfluid amplitude. So it signals that maybe by approaching the phase transition, the vertices behave differently in one class. So I want to develop a tool to see how many different amplitude of the superfluidity we have in this system. So for example, look at this random number. So I plot it here. You can see there is a 3 different structures at once if you look at this. So what I did is that I first re-scaled these numbers between 0 and 1, and then calculate difference between each, and then sort it, and then sort each number, and then calculate difference between each number. So for example, here I calculate its difference and right here, and difference between these 2 numbers and right here, and so on. So I call this number gap of between these numbers. So now find the number of gap with amplitude larger than some amount. For example, here I choose 0.2, and I found 2 different gaps. So here I found 2 different gaps in this structure. Therefore, by this way, I can count number of different gaps in the amplitude distribution of the superfluidity amplitude. So if we do this for different hopping strengths, you can see that it increases by by approaching phase transition. So again, signaling that different vertices behave differently near phase transition. I mean, become more distinguishable in phase transition. So I show this NOG, number of gaps for the superfluidity amplitude in logarithmic scale, and you can notice that it also has some power law near phase transition. So it may be new exponent in the for the quasicrystal in phase transition. So therefore I found NOG, number of gap, proportional to J minus JC power some exponent, which here I obtain it minus 0.9. As you can see from order parameter, which I show average of order parameter, it is a second order phase transition, and therefore we expect correlation length in this system also diverge by this this behavior by exponent minus 0.5. So I want to know, is there any relation between number of class that previously in vertex classification we obtained and number of gap which find in the Bose-Hubbard model? So I can say we can suggest that NOG, number of gap, means that number of different vertices, which was number of classes. They are proportional together, and we saw before that number of classes also proportional to K power some number, which we previously obtained 1.84. And also, I previously said that we need a length to distinguish different vertices in the quasicrystal. So maybe in the phase transition, classify vertices done by correlation length, which is the length that the two different vertices can touch each other. So if we change K to correlation length and using this equation, this exponent relation, here you can find NOG proportional to J minus JC power minus 0.9. Such a exponent. This is the things exactly we derive here. So we can conclude that NOG, it seems that proportional to NOC, and correlation length classify vertices order parameter. This is a Bose-Hubbard model. I want to see, can I see this conclusion in the other model? So I study Ising model, and I use mean field equation to see the mean field behavior of the 2D Ising model. I define a vertex model of the Ising model, and this is a ferromagnetic interaction. And I look at the magnetization by increasing temperature. So you can see at the phase transition, the order parameter or magnetization distribution takes a similar shape if you compare with the Bose-Hubbard model. So it seems that they have a similar origin. And interesting things, if you also calculate NOG for magnetization, number of gaps between data of magnetization, in terms of temperature, you can find also a scaling behavior team with exponent around 1. So it is very near, close to 0.9. Therefore, it seems that the correlation length also here play the role of the vertex classification. I want to know that if I change this NOC, you can see that you have seen that I use this NOC scaling power law behavior and justify the appearance of this NOG power law behavior. So I want to know if I change, if is this NOC relation change to something else, what NOG I can get. So artificially, I study mean field as in one-dimensional system. The system don't show any ordering in because it is one-dimensional. But I just want to study this mean field equation in one-dimensional for Fibonacci sequence, which is given here. So I show you previously that NOC here has a relation. Okay, this is K, not R, which almost its exponent is half of the Penrose. So if NOC is related to NOG, its power, its exponent should be half. So we can see if we write NOG of this system, it also becomes half. So we can conclude that NOG, I mean number of gap in the distribution of the magnetization or order parameter controlled by number of classification exponents. So until here, we can conclude, I mean, this is just for mean field. And I want to know that if we change universality class to other universality, can I see again such a thing or not? So I studied 2D Ising model in Penrose lattice, and I use Wolf algorithm with 6 million measurement and update every 10 flip per site. So I can find the phase transition by looking at CV, which is located at 2.4. And if you see the magnetization in terms of temperature, you can see that the universality class somehow I obtained the correct universality class of the Ising 2D Ising model. And if you look at the number of gap versus temperature, you can see near the phase transition it becomes flat. So it means that exponent of number of gap of the 2D Ising model is around 0, something like that. Okay, I think I make it. Yeah. It becomes flat near the phase transition. So and if you look at the perpendicular space representation of order parameter, you can see near the phase transition, before the exactly at the phase transition, you can see that perpendicular space also has some structure, but it does not have any fractal structure in it. So it is very strange actually for me. It seems that maybe appearance of fractal structure is due to just mean field calculation. So this is my conclusion. Quasicrystal may be introduce new scaling behavior in phase transition, but relation between NOG and NOC is very, I think, challenging. I want to look at the 3D Ising model and to see NOG if they are related really or not. So thank you for your consideration.
So thank you for nice talk, and thank you for your attention. So now the session is open for the discussion and the question or comment. Is there any question?
Yes, I have a question. I have a question on regarding the first part of your talk. Is it possible to see a similar fractal structure at the temperature just below the critical temperature?
For the Ising model?
No, for the Bose-Hubbard model.
Actually, I didn't study the Bose-Hubbard model with temperature. I just studied with hopping model. I mean, I mean quantum phase transition. But I think because you are using mean field, even if you want to look at the temperature effect with mean field, because your system is very large, you are using some mean field equation. Then I think you get similar fractal structure, like Ising. I mean, like Ising that here I show here. I think any mean field equation. I mean, I think any mean field equation show this fractal structure, even if you calculate. I mean, considering thermal phase transition or quantum phase transition.
So I wonder if you can see a similar fractal structure for a simple VEC in non-interacting system on Penrose tiling.
Oh, VEC. Okay. Well,
Or does the mode criticality is the mode criticality important in
actually about the real situation I cannot comment about, because as you see in the Monte Carlo simulation, we didn't I haven't seen any, I mean, critically in phase transition. Therefore about real situation, I mean, considering VEC in the I mean considering all of the quantum effects, maybe there is no fractal structure. But if you consider it with mean field within mean field equation, I think you can see fractal structure.
Okay, thank you.
Thank you.
Okay, so any question or comment?
So I have 2 questions.
Thank you.
So very nice talk. And first question is you find so new kind of scaling, and so experimentally how to access that kind of scaling. So if you have an idea, please tell me.
Actually, here I show NOG, number of gap, in terms of the hopping, strength for I mean large threshold of the gap detection. So even if you choose if you choose a very large threshold for finding the gap between data, you can see some scaling behavior in this system. Although maybe the exponent is different, but you should see this divergence of the NOG in this in the experimental setup. This is my suggestion, because here I just use a very large threshold for the calculation. Therefore, I suggest maybe we can see this in experimental setup.
Okay, and the second question is you compare the quasi-crystal and approximate in the Monte Carlo simulation.
Yes.
So can you get some difference of these 2 systems? So quasi-crystal and approximate in Penrose case.
You mean that real quasi-crystal structure?
No. Penrose case. Penrose quasi-crystal case and the approximate case.
Penrose quasi-crystal and approximate of the Penrose structure.
Yeah.
Am I right? Actually, I don't think the phase transition changed. I mean, the location of the phase transition changed, but maybe fractal structure. I think fractal structure, appearance of the different distribution of the order parameter change in this system. But I don't think, because the system is very large, you can around 100,000 sites. So I think it's somehow near the, some thermodynamic, not thermodynamic, but it is near the real quasi-crystal structure. So I don't know, maybe actually. Okay.
So
actually,
sorry. Please tell me.
Actually, people also, I know a word that using GPU calculation and calculate this transition for 20 million sites. So there is no change in universal, either in universality or location of the phase transition.
Okay, thank you. And so power law, so the exponent is basically is the same between the two systems, right?
Yes, universality did not change. It will not change by
Okay.
changing the cohesive.
Yeah, depend on university. Okay, thank you.
You're welcome.
So is there any question or comment? I think a naive question is also welcome from a student.
So I have two questions.
Thank you.
And both have a section of the both have a model. And so previous slide, the critical behavior in the multi-initiated and superfluid phase diagram.
You mean this?
Yes. So, and the multi-initiated state in the order parameter of the superfluid is 0. So when we change the J, so the way beyond the critical point, so immediately the order parameter is classified by the many grouped in the beyond the coordination number.
Actually, by change, I calculate Vita accuracy 10 power minus 10. So immediately after it takes non-zero value, it gives this shape for the distribution of the order parameter.
Yeah.
I don't know. Sorry, I missed your question. Could you please?
So the my image, so we change the and J is very small. So the order parameter is grouped by the coordination number. So but this result is in the reverse result. So
I slightly changed the J for the this line. Actually, I investigate all of the line because here we know that in both Howard term, this peak of this Mott dome has a different universality class, but we cannot resolve this in the mean field equation. We have to. We have all of the points give a similar phase transition, similar mean field universality class. Therefore, for all of them, I get similar exponents and similar conclusion. It is not depend on the location of the mu and j. Although there is a difference here, I mean, in integer filling that this story doesn't appear in this integer filling.
Thank you.
Okay, so is there any question or comment?
So I have a naive question. So you showed us capital K. K is a link number?
K, okay.
So
here,
sorry.
No, sorry. Okay, here I use a classification, yes, and first I look at surrounding area of this 7, and then I construct a structure, I cluster with one link, and then I construct a structure with 2 links. K is this number of links which we make a cluster. Here is 0, here is 1, and here is 2.
Okay, so this link number is you say proportional correlation length. And yeah. So my question is that relation is why depend on the universality class? So can you explain?
Actually, this is my suggestion. Someone should. This is a length in the quasi-crystal. So we have just one length in the phase transition, which is just correlation length. There is no other length. So I mean, exchanging K to correlation length coming from this view that in the phase transition we just have a one length govern the whole of the system. So we can ask why K should depend on correlation length. We cannot ask about why this should depend on this, but we can ask about what is the exponent of this. So one view is that this may be some percolation physics, and this exponent should be half or some other exponent. I mean, this relation should be with some other exponent. But here, if I want to justify this physics, I should I just use K proportional to correlation length. But I think maybe if we change the universality class, maybe for 3D dimension, I mean, beyond the mean field calculation, maybe this relation changes. For example, I don't know, in the Monte Carlo simulation, maybe K is proportional to, I mean, chi power 0. So actually, I cannot comment on this relation. I just, this is my view that there is one length should be classified each vertices. Which this length is correlation length.
Okay, I see. Thank you.
Okay, so any question or comment? If no, I would like to close the session today, and thank you for close attention. Your close attention, and if you have additional question, please do not hesitate to directly contact with Rasoul.
Thank you.
So thank you for your participation.
Thank you everyone to listen to me, to giving this opportunity to me to present my work.